Hi there. I gave this talk a few days ago down at City Centre, and there was quite a few people were unable to attend on that day. So I thought it would be quite nice just to make a recording so that people who did want to have a look at it could review it just to see where we got to in our conversation. Now, what I want to do in this talk is just basically give you a brief overview, almost as a beginner, of how statistics is presented in research. It's certainly not intended as a deep dive. So let me tell you about myself. My name is Philip D and I work in the Academic Development Department, which is based in the Faculty of HLS, Health, Education and Life Sciences. But as I said, this was a talk which was cross-faculty to postgraduate students and to staff as well. So it is intended for a wider audience. The intended topics I want to go through is an acknowledgement of how research is apparent in both our reading as well as in our doing. Obviously, I'll expand upon that. I want to dive into also the language of research, which I think for me is one of the first barriers that many of us come across in statistics, in research, and therefore I think it needs acknowledging and dealing with early on, or at least addressing in some description. Talk of description, the two broad areas of statistics dealing with numbers in research are descriptive statistics and inferential statistics. So I at least want to give you a flavour of what they mean and what the differences are between them. Then I want to say a few brief words about the typically used and more popularly used types of software to help people with their analysis in quantitative research, and then end by giving a few recommendations of resources. In the class we also had a bit of a discussion about what should we do collaboratively as a group next, and I might make an odd comment or two about that. Okay, so let's dive in. Even if we are not yet doing research, we are still a consumer of research because we're constantly being expected to read the research material out there. And this is true whether you're doing qualitative or quantitative. We're going to be exposed to a lot of information, a lot of technical information, and that can be very, very daunting. Now, although my expertise and the thrust of this talk is all about quantitative research, I would still acknowledge or recommend that even those of you who are interested primarily in qualitative research, it's still in your interest to be familiar with the quantitative research landscape. I mean, once you've got a research question in mind and you're doing a scoping exercise to see what's been written recently about that in the research literature, you're likely to come across both qualitative and quantitative research, and therefore it'll be more power to your elbow if you can A, make sense of, and B, maybe even critically appraise the quantitative research as well. So I think there's no excuse to say, well, it's not of interest to me. I think it's beholden to us to understand the fuller range of the main paradigms in research broadly. So with this interest in mind, this thought in mind, I found really randomly an article. It's obviously it's health related. It's the effects of respiratory rehabilitation before open cardiac surgery on respiratory function. It reminds it's a randomized clinical trial. It's a sort of paper many of us find ourselves reading, sometimes with great difficulty. Let's see how numbers appear in a relatively typical paper. Well, here's their abstract. And please feel free at any point in this recording to pause and think. But where are the numbers? Well, it tells us that there were 60 patients, okay, and then it tells us how the groupings was 39 males and 21 females, and gives us that in percentage. So far, so good. I think most of us would be quite happy with that. It gives us the mean age with this curious plus or minus. Now, we did notice, and we discussed this in class, there must have been such red faces when this paper came out that we learned later on in the paper that the average age was about 50 something. So what was going on with this mean age, I don't know. It's a typo. Of interest to us is, what does that plus or minus 9.56 mean? Well, it sounds like an error. I'm an ex-physicist, so I read that as an error, but actually I'm pretty sure they mean it to be a measure of spread. And we'll talk about this later, but I'm pretty sure in this case it's 9.56 as a measure of standard deviation. Obviously more about that later. What else do they give us? They also give us something called a confidence interval, and they say the confidence interval of this measure of predicted peak flow indices is 1.9 to 9.4. So we're thinking, okay, there's possibly two items on early on, even in the abstract, that makes us think, I'm not sure what that means. Now, if we don't know what it means, we've all done this, we just tend to skip over and go, well, I don't think I necessarily need to know this detail, or I hope I don't need to know, and I can move on. I can understand that position. I've done it myself many, many times. But there's always a nagging thought, how important was that number I ignored or whatever? And if you don't if you don't understand something, then you clearly are not in a position to appraise it, to critically appraise it. So I would feel, and this will be my guiding spirit for this talk, that I am cherry picking terminology and stats concepts that I think are important enough just to put on your to understand list, put in your bucket, as it were, of things I kind of really ought to conquer. So I think measures of spread is definitely one that I think is important enough for you to make that effort. And I think because it comes up so often, this concept of the 95% confidence interval, I'll obviously be addressing both of those a little bit more detail in a while. Okay, sticking with the same paper. This is very common in a piece of research. You get tables summarizing their data, and you think, okay, with a little bit of care and not rushing, I can work out what's going on here. They're giving us many measures. It's got the age, the gender, the smoking, BMI, whether they have or haven't got diabetes, etc. And you have to understand that this also gives a clue, what's known as a legend, of what's going on with the numbers. So for the age, they're telling us that they're giving the age in years, and it's the mean value they're giving us. This is why I knew that number of 8.1 was wrong. That's 54.4 is the mean in the expression group and 59.3 in the control group. Okay, and the number in brackets on this particular line is the standard deviation. And you can see the standard deviations are quite similar. Similar with gender, smoking, etc. They tell us what the measure is, frequency, and then what the thing is in brackets. So in this case, it's the percentage. So far, so good. One thing which won't be familiar to very many of you is this very last column, something they're calling the p-value. And again, I feel the p-value, rather like the confidence interval, yes, maybe one of those slightly less familiar concepts, but definitely on my list of things I feel we need to understand even as consumers of research, because we don't want to be a passive reader, a passive consumer of research. We want to be an active reader where we are asking questions of the text. We are asking ourselves, do we agree with conclusions drawn, etc., etc. We can't do that without a certain amount of deeper knowledge. So I think the p-value definitely goes on my list of things I want to understand, but we'll talk about that later. The final table I'm going to get you, and this is where most of us in a paper will just, our eyes will glaze over and just think, you know what, turnover. I do get that, because there's so much going on, it's so dense, but they've summarized their data for a purpose, and that is for us, the reader, to extract, focus on the items of interest. Very often as a reader, we're not interested in every single aspect of that research, but perhaps one or two key variables, one or two key measures. And so we might just home in on the bit that we want to look at. But this is something when we read a paper, we could very easily come back to again and again. One thing I didn't mention, let me just go back to the previous one, is those p-values all were positive. It turns out p-values are only ever positive. But with these things called confidence intervals, which we saw in our abstract, and I know it's confidence intervals because it tells us that the comparison between groups, so these are these values here down this last column, it tells us that in brackets they're telling us it's the two values are the 95% confidence intervals, and you'll notice that some of those are negative. So I've just noticed that, not necessarily understanding yet what's the relevance, but I think my message to you would be, don't panic. Look at the information carefully, obviously in line with what they're seeing in the text, because the text will often refer you back to the table. And don't be afraid to look at it a little bit, then perhaps come back later once you sort of have further questions to ask. Certainly when they get to their conclusion stage, you might come back to a table like this and say, to what extent do I agree with what they've said? Okay, so let's move on now just a moment away from numbers, just to get our breath back. And I want to talk a little bit about the language. As I said earlier, for me, a lot of the jargon is an initial barrier for many of us. So I want to talk about the language, the jargon that is associated with this idea of variables. Well, that word already, variables, is a jargon word. And what it means an attribute. So if I'm talking about a person, an attribute, a variable that I could measure, might be that person's height or weight or age or blood pressure. It could be their life expectancy or their recovery rate. Now, there will be examples of quantitative variables, which are variables, attributes, which naturally lend themselves to measures using numbers. But you can also have variables that are inherently qualitative, like hair colour, eye colour, how they feel, what their level of happiness or depression or mental health. Those sorts of questions are clearly of a more qualitative, subjective nature, whereas quantitative tends to be more objective. But I do feel that in both cases, that idea of the variable, the thing that can vary from one person to another, or even vary within a single person over time, explains why it's called a variable. But we have to understand that that sense of those two broad paradigms also is reflected right at the heart of my opening piece of jargon, the jargon of the word variable, and then a sub topic of, well, what is a qualitative variable, what is a quantitative variable. Another pair of terms I want to discuss with you is the idea of the discrete versus a continuous variable. And now this is only referring to quantitative variables. Now, discrete variables are numerical values that can only take certain permitted values. They tend to be whole numbers, like how many people voted for political party A or B, or how many children in your family, that kind of thing. In actual fact, I can think of at least one example of a discrete variable where you can have decimals, and that would be shoe size. In the UK, shoe size, say for men, might be 8, 8.5, 9, 9.5. But they are the only permitted values. You can't walk into a shop and say, I need a 8 3/4 or a 9 1/4 or a 9.1. That's not how it works. So they would be classed as a discrete variable. They're clearly not as sophisticated as what's known as a continuous variable, a continuous measure, also numerical, but that will be something like weight or height, where in principle you can measure or remeasure to ever greater levels of precision. And typically the presence of decimal places would give the game away. We saw an example that was an exception to that rule with shoe sizes, but certainly with continuous, if something can go decimal, if something can be measured to a high level of precision, then you're in the regime of continuous data. Now, don't think that just because a data value was a whole number means it has to be discrete. If someone says to me, how old are you? And I say, well, I'm 61. Well, that does not mean I'm exactly 61. It just means I haven't bothered to tell you how many days and months beyond 61 I am. So the variable of age is inherently a continuous variable, even though we tend to record it as if it was discrete. So there's a subtle difference between the two. But I'm giving you these definitions because I know they are important concepts, and therefore I know they're going to come back later on in terms of other types of measures, both in terms of descriptive and inferential statistics. So I'm not just plucked these out of the air. Okay, on to the next jargon set, and that is that all data types, numerical data types, are not created equally. There is a hierarchy, a sense of a greater level of sophistication. There are 4 areas. So at the bottom, we've got our nominal level data. Often that's also called in the textbooks categorical data, which kind of gives it away. Then you have ordinal level data, the next one up, and then we have interval level data and ratio level data. And this hour gives the sense of less sophisticated to more sophisticated. So you can see that interval and ratio level data is considered more sophisticated, more useful, if you will, than ordinal or nominal. Right, let's unpack these. Now, nominal level data, I said it was also called categorical, is often when you have categories like male, female, which football team is my favourite one, who I voted for in the last election, that kind of thing. Now, typically, you would only be able to count the frequencies within those categories. Certainly statisticians, when they are coding data, they might assign like the number 1 to male and the number 2 to female, but that doesn't inherently have any intrinsic meaning numerically, only that it was a convenient sort of label to give. Importantly, it is these nominal level variables that are often our grouping variables. So I might say, look, I'm doing an RCT, a randomized control trial, and my nominal variable is the extent to which I gave some intervention, like a new drug. So group A might be a placebo, no drug, and group B might be my intervention drug. So my nominal variable, my grouping variable in this case, would be the grouping. But you can still do work, you can still do a bit of statistics even with nominal level data beyond just saying these are my convenient groups to compare later. The ordinal level data is classic ranking data. If ever you've been asked a questionnaire and you've been asked, how do you rate this product, good, better or best, or how do you feel about this statement, strongly disagree, moderately disagree, neutral, agree, strongly agree, that is the typical ranking data. That would be called a Likert scale type of question, and that's where the coders, the statisticians, might say, right, I'm going to code a 1 for a strongly disagree, a 2 for moderately disagree, 3 for neutral, 4 for agree, and 5 for strongly agree. Again, the numbers don't necessarily have an inherent value, although now the numbers have reflected at least the ranking. But there's more you can do with ordinal level data. It's not as good a data as what you could have, but it is very, very common in surveys. Let's keep going. Interval level data and ratio level data are so similar that very often textbooks, certainly textbooks for beginners, doesn't even distinguish between the two, and will often use the word scale to mean either of those. But there is a difference between the two. Certainly they are both measures that we would recognize as something: your age, your weight, height above sea level, that kind of thing, degrees centigrade, whatever it happens to be. But the only subtle difference between the two is the fact that interval level data is a relative type of measure. It is data where there is what you might describe as an arbitrary zero. Think of the temperature. In the UK, when we're looking at weather charts, the temperature outside is often given in degrees centigrade. Well, we know we can go colder than 0 degrees centigrade. We can go minus. So clearly it was just a convenient scale starting with 0 and going up to say 100, which is the boiling point of water. But we know the scale extends in both directions. So that 0, in this case the freezing point of water, was just a convenient one developed back in the day. The example I give here is height above sea level, the height of a mountain above this puddle of water known as the sea. Well, why we didn't decide to do the height of the mountain from the very top to the very bottom when the mountain stops going down. You think, okay, but we just happen to do it with respect to sea level. That makes it interval. Ratio level data is where 0 means 0. You cannot go negative. Keeping with our temperature example, that would be degrees Kelvin for those of you who did science at GCSE. But also things like weight and height, they will be ratio level data. 0 means 0. I'm not saying that the measure can go 0. Your weight will never get to 0, but it is a measure with respect to 0, and therefore it's ratio. I've only mentioned these because you will see these terms come up in the textbooks and also come up in research papers. Okay, the last pair of jargon terms I want to mention is independent variables and dependent variables. Now, these are used most commonly in experiments, in trials, say randomized control trials, but they can still also be used to some extent when you have observational studies. The point is this: the independent variable is the variable that you yourself either control or choose. So it might be the amount of water. I might have, say, my independent variable might have 3 levels: no water, small amount of water, a lot of water. But I have chosen that as a researcher. If I was observing, I might then choose to look at, say, IQ, recovery time, you name it, with regards, say, gender, or with regards say, ethnicity. I've chosen that, and so I would still argue that that can be seen as an independent variable. The dependent variable is a thing you have a lot less control over. In fact, virtually no control over, and that is a thing you might be measuring. In this case, on this slide, you've got, say, the height of plants, or it might be the amount of fruit you get. And you're saying for each of my levels of independent variable, I'm going to measure the output, measure, say, the height of the plant or the amount of fruit or whatever that I get. So the dependent variable is the output variable, the thing of interest. The independent variable, what I might call the input variable, is the thing that I manipulate or I have to some degree chosen. A couple of examples might be babies. I might be saying, okay, I'm interested in, say, the birth weight, and so my independent variable possibly could be gender, and I might just go with the slightly old-fashioned view of, males versus females. I know that can be a little different nowadays, but that will be my choice of grouping I'm looking at. Certainly, I don't choose whether any individual baby is a boy or a girl, but you get the idea that I've at least decided that gender is going to be my grouping variable, and then my outcome variable might be the dependent variable. Obviously, this links into some hypotheses I might have about, I wonder if there's a difference in birth weights between boys and girls. Another slightly less serious example might be something like this, where my independent variable will be the force on which I pull on the line's tail. Then the outcome variable, the dependent variable, might be the recovery time of the unwise gentleman in intensive care. But you kind of get the idea. So I'm hoping that that relatively brief discussion of what I feel are the more pertinent starting concepts, and certainly the jargon ideas in the statistical region, statistical sort of relationship of quantitative research. I'm hoping that it at least gives you a little bit of reassurance to think, okay, I'm off to the races. I'm starting to hear these terms, and I'll become less fearful. Sometimes it's a good idea to create and maintain your own glossary. I know I did that when I was learning these things, because you constantly forget it and I'm to look it up. So I just had a little notebook where any new terms I thought, that sounds important, I'm going to make a note. Okay, I want to move on now and talk about the two types of statistics, descriptive statistics, and then we'll go on to inferential statistics. Now, descriptive statistics is something that we will have all seen at school, probably at Key Stage 3 or even at GCSE. Obviously, for many of us, that's a long time ago. You see, for any measures that we do, typically we'll do it over a group of participants or whatever. We want to summarize. We are always looking to summarize our measurements. And to summarize our measurements, we need two values, two summary values, in order to sort of say, this is what my data generally is showing. Of course, you've got your raw data, but you're not going to show that in a research paper, and the papers aren't going to share that with you either. Those two measures are some sort of measure of average and some sort of measure of spread. Okay, so that idea of the average taken one at a time, I've put two other terms on there because statisticians and researchers, boy, do they love their jargon terms. So as well as the word average, a word we all know, the textbooks will often use the phrase central tendency or location to mean the same thing. Confusing, I know, and it sort of makes me a little bit sort of exasperated. But we need to understand what we mean by an average, so what is an average, and then if there's a choice, which average should I use? Now in classes, I often show this data set, and you might pause the video in a moment, and I say to the students, like, what do you think the average of that data set is? And there are 1, 2, 3, 4, 5, 6, there are 7 values. So have a little think about it, pause if you wish, think about what your answer is. Now most people in the class would say they think the average is 3. Because I added up those 7 values, they got 21. And they thought, well, 21 divided by 7 is 3. My average is 3. If that was true, if that was the only measure of average, then this statement would be true. But this statement is clearly not. Obviously, it's tongue-in-cheek, but clearly it is poking fun at that one definition of average. I'm sure many of you know of other measures of average that there are, and that therefore from this data set, I'm going to share with you 3 common measures of average. There are, in fact, 3 different answers I would get when trying to extract the average from that, which of course brings its own problems. And that is, hang on, if I've got different values coming out, it sounds like there's no one average, so we're going to have a little think about that as well. Okay, so when we measure the average, there are, as I said, typically 3 common ones. One that we thought about a moment ago when we add up and divide, that's called the mean. Then you have the median, and then you have the mode. And you probably remember those 3 phrases without necessarily remembering what they all refer to. Now, briefly, the mean, what we've seen, is where you add up to find a total and divide by the number of values. That's your mean. What makes the mean interesting or powerful is that it utilizes every value in the data set. A limitation might be that outliers, like a particularly big number, that number 11 in those otherwise small number, will possibly pull up the mean. Or another point to make is that the answer that you've given the mean might often be a value that didn't even occur in the data set, because often the mean comes out to be some sort of decimal point. So there are strengths and weaknesses for each of these. The median is one where you put them all in order, lowest to highest typically, and then you find the middle value. There are subtleties if there's an even number. If there's an even number of values, then you appear to have 2 middle values, but then you split the difference. The mode is where you say which is the most common value. So let me just go back to my data set. We know that the mean was 3. The median, well, if there are 7 values, there is only 1 middle value here, which is the number 2. So the median is 2. And I hope you can see that the mode is the number 1. So there are 3 different values there. So we have now created another problem for ourselves, which is when to use which average. We need to have a think about this. And by the way, if you're thinking, Philip, I need more help on these concepts, well, I will place at the bottom of this video a link to videos that will go further. I've done a whole series of videos on some of these concepts, so I'll link you to further materials should you need it. But let's start with a tentative answer about when to use which average. I'll tell you in a moment why it's tentative. If our data is only nominal, or what's known as categorical, then there is only one average open to us, and that is the mode. And you see that in the same bar chart. The tallest bar, that's my average, that's my mode. But I've only got one choice. If, however, think about that hierarchy of data types, I've got an ordinal level data, then I can use the median. Usually you would look to be using the most sophisticated measure, and so for us the median would be the better one to use. But you're still not forbidden to use a lower down one, as it were, the mode, and sometimes people prefer that. I've put a star here because some ordinal measures, like I've seen this in tools for measuring pain, where instead of asking you to tick a box about how much pain you have, they'll have maybe a line and invite you to put a mark on the line where your pain value is, and one end of the line might be 0, meaning no pain, and there might be 10 at the end saying excruciating, excruciatingly painful, and you might put a mark. So you could end up with data that, although it feels ordinal at heart, might actually be generating a number with decimals, etc. And so you might sort of have to already modify that thought. You might go to the higher level of measure of average. If your data is interval or ratio, then you would usually go with the mean. But of course, you can still go with the median or the mode. Now, these are all it's like a sort of a staging point where we say, this is from the information we've got so far, these are the rules. But these rules might be modified, because one thing we've not spoken about is something called the shape of the underlying distribution. I will say a bit more about that later, so that at least you're sort of able to sort of say, okay, I got this far. What's Philip got to say about modifying this? Because we will modify it slightly. So we've given a bit of a discussion about first of those 2 summary values, the average. Let's now talk about that second summary value, the spread. Another word you'll come across for that is the dispersion, means the same thing. And we want to ask ourselves the same 2 questions. What do we mean by spread? What is the spread? And then if there's a choice, which spread should I use? Flora or margarine? No, which the concept should I use? Well, again, like the average, there are 3 common measures of the spread, which you'll probably recognize a couple of these from your school days. You've got the range, the interquartile range, and the standard deviation. And again, I'm not going to go into great detail because I've done a whole video on this, which I'll put in the as a link below. The range is the one where you say, well, what is the difference, the distance between the smallest value and the largest value? If I'm looking at, say, the age group, and I've got the oldest person in my participant list was, say, 50, and the youngest was 25, my range would be 25. Good researchers not only tell you the range, but they also might put in brackets what the lowest and maximum value was. So if it was age, I might say the range of my group was, say, 80 brackets 20 comma 100, something like that, so that the reader can understand, yes, that's a big spread, but also get a sense of what your upper and lower limits were. The interquartile range is very similar to the median, where you put them in your numbers in order, but what you do before finding the median is you split the data exactly in two. And you find the median of the lower half, call that the lower quartile. You find the median of the upper half and call that the upper quartile. And then, like the range, you just take the larger from the smaller, and that will be your interquartile range. A real strength of the interquartile range is that it is insensitive to outliers. If I've got an outlier that's a very large number, it will not impact on the interquartile range. It definitely will impact upon the range, but the interquartile range is a value that has great uses in that sense. And the most sophisticated one you'll come across, and most of you will have heard of this, even though you might struggle to remember maybe the formula or what it means, is the standard deviation. This is rather like the mean in that every value in the data set is used in its calculation, which therefore means outliers might push it out a little bit. But typically, on a relatively well-behaved data set, the range is the largest measure of spread. The interquartile range, the IQR, is a bit smaller, and the standard deviation is usually smaller still. And you'll notice that I've given you two labels for the standard deviation. They often use the Greek letter S, known as sigma, if it's a population parameter, and S or SD, using Roman letters, to mean a sample parameter. So if I'm measuring the standard deviation of my sample, I'd usually refer to it in my writing as S or SD. But if I'm talking about the spread of the population, the standard deviation of the population, I would generally use the Greek letter sigma. And just to frighten you, this is one of two possible formulas to work out the standard deviation. This all takes place, of course, behind the scenes. Whatever package we're using, and I'll mention those a little later, we just need to know what should I be asking it to calculate and then make sense of what the answer is. But this isn't that frightening. You see, xn just means the value of my data. So if I got 10 values, I'm going to have 10 lots of xn. I'm going to have x1, x2, x3, x4, right up to x10. X bar, well, that just means what was the mean of that particular data set. So all that numerator is doing is saying, for each item, I tell you, there's something missing here, which is a sigma. There should be a sigma there. I'm going to put that into my slide later on. But yeah, so apart from the slight typo there, it is essentially an average of the difference or the dispersion of each value in the data set from its mean. And because there can be some going below and some above, you'll end up with negatives and positives. And if you're not careful, try and average out negatives and positives, you tend to get zero, hence the squaring. Back at school days, we knew that if you square a value, square a negative, it gives you a positive. And you kind of divide by the sample size, and then you take the square root to get rid of that square sign. It's obviously a little bit more complicated than that, because the question might be yn minus 1, but I'm going to leave it as it is, simply to say there's a formula, and even though I've just expressed it incorrectly, I'm going to get over that. It's one that is going on behind the scene. So again, tentative slide here saying which measure of spread should I use. If my data is discrete, I will either use the range or the interquartile range. And if my data is continuous, I will typically use the standard deviation. And I put here or below, because I'm still allowed to run the range or interquartile range in my data is continuous. Okay, I want to pause there because I'm getting a dry throat. I wonder if it allows me to pause the recording. Oh, it doesn't. But I suggest that you yourselves have a little break there. Pause the recording yourselves so that you can go and grab a cup of tea and then come back, and then we'll go on to inferential statistics. Okay. Okay, we've dealt briefly with descriptive statistics, which is where we effectively summarize what we found. Inferential statistics, for my money, is the more important one. It's like saying, well, what does it mean? It helps us to form conclusions. And at the heart of inferential statistics is the idea of something called significance. Now, significance in everyday speech means importance, and there is a role clearly for that in quantitative research, but we have to be careful because there's two types of significance. There is clinical significance, which is where we have to ask ourselves the question, was this change seen, e.g. before and after, or between group A and group B, was it important in my terms as a professional in my profession? But the other question is known as statistical significance, and that is, could that change that we've seen, that we've measured, could that be a fluke? Could that just be some sort of random noise? In other words, is the change we've seen, is it real or not? And it is statistical significance, which is the realm that is dealt with by inferential statistics, whereas clinical significance is the realm dealt with by yourselves as readers, as practitioners, where you'll say, do I agree with the conclusion given that this is a big enough difference for it to be important or to change my practice? So let's deal with the first one, clinical significance, because as I said, I think it's the more intuitive one, but it is an important one. Well, it is, as I've said, down to a question of judgment, but context is important. Let me give you an example. And in the class, I always get a very similar answer. I say, look, without any context, let's imagine I've got two groups, A and B, and I've measured something. And in group A, that average was 48.1%, and in group B, it was 51.9%. I said to students, intuitively, do you think this is going to be of clinical significance? And most students go, nah, because the numbers are very close together. And I'll say, well, if I reveal what the measure was or of about, they'll go, oh, hang on, can I change that evaluation? Because this was very, if you want, clinically significant, practically significant. It was very important because although the measures were close, the vote was close, the consequence was huge. So this is why never just be guided by the numbers when evaluating clinical significance. Always say the numbers in line with what I am interested in. If I'm a nurse, palliative care nurse, and I'm looking at new drugs for, say, childhood leukemias, and I find that drug A has a 1% improvement over drug B, I might say, well, hang on, I'm saving one extra child per 100. So for me, that is hugely important. Yes, please, I want to buy that particular drug. So it's going to be something different for me than for someone else in a different sort of field. So clinical significance is very important. But before we can allow ourselves to make that evaluation of clinical significance, we must first establish statistical significance, i.e., could it have been due to a fluke? I mean, imagine I run an experiment and I run a series of lectures. And so what I do is I have a baseline measure, say in stats, and then one at the end of my series of lectures. So imagine at baseline, I've got, okay, 45% was my baseline average. And then after, say, 6 1-hour lectures, I've got a class average of 51%. I might say, oh, it's improved. Good, give me a pay rise. My boss might say, hang on, 2 points, Phil. One is you've only had a 6% improvement. I'm not impressed with that. But the other might be, could other things have caused this? For example, there might be someone in the class and she's very, very good at statistics, but she simply wasn't there for the baseline test, but was there at the end. She could have brought up the average. She could be the outlier. There are issues like that that I sort of would want to investigate before saying we have statistical significance. Now, it can't just be down to someone's gut feeling. And this is why we have statistical processes known as inferential statistics to help us evaluate that. So, asking the question, could it have arisen by chance or some other factor, is at the heart of much of what we are calling inferential statistics. There are going to be lots of different tests, and I will show a few of them to you a little bit later. But each of these inferential tests spit out, amongst other things, something called the p-value. So it will guide us into answering that question, could it have occurred by chance? Now, the p-value is just a probability, and we'll say a little bit more about that in a moment. There's another measure, and this links right back to that abstract I showed at the beginning. There's also a way of establishing statistical significance if we look at confidence intervals. And this is not just confidence intervals, but crucially confidence intervals of differences. So let's just take each one in turn. Okay, the p-value, and it's not how it's illustrated here, as I've already said, P stands for probability, and it is essentially not entirely accurate, but it is good enough for us. It's essentially the probability that the result we obtained was by chance alone. Okay, and typically that's going to be an agreed value of, say, 0.05. Now, this comes from the concept of the distribution, so I now need to bring that in. Imagine I'm measuring something like the heights of school kids, like the heights of all boys in year 11 or something, and I plot it on a bar chart, something like that. I quite commonly get something like this, which is unimodal, has a single peak, and it is symmetric. Not all distributions are, but many of them are. And there's a very common type of symmetrical distribution known as the Gaussian distribution. And the unique feature of the Gaussian distribution, otherwise known as the normal distribution, is that the mean, the median and the mode are all the same value. And it's because of the symmetry. So this is the one that's been studied most by mathematicians. Okay, as it's so useful, mathematicians and statisticians have studied in depth the characteristics of this distribution, and they found that if you look here at 0, which is like the point of the mean, the point of the peak, and they say, look, if we went one standard deviation above and below the mean, they worked out that just over 2/3 of all the data will be collected within that central block. If they go 2 standard deviations above and below the mean, they've captured 95% of the data. This is the link to the magic p-value of being 0.05 or 5%, because it means if your data lies in one of these upper or lower tails, then you're outside that 2 standard deviations. And for most inferential statistics, they will call those the critical regions and say that they are the regions that we can therefore reject the null hypothesis. So the most common one is the 5%. So if your p-value is at or below 5%, at or below 0.05, then you can declare your results to be statistically significant, and then you can say, right, I am now going to go and ask myself the far more interesting question of clinical significance. But we mustn't do the other way around. If you haven't got statistical significance, if your p-value came above, say, 0.05, then you can't reject the null hypothesis of there being no difference, and therefore you can't make any honest statement about clinical significance, because the likely chances that your data was just due to a fluke. Now, of course, other distributions can occur. So, for example, I've done lots of marking in assignments at university level, and very often you get a distribution like this. Because you might have a pass mark, say, for the MSc, our students have a pass mark of 50%. So the great majority of students will have a higher value, and you'll have a low tail of people not doing so well at the lower grades, but only a sharper cutoff above there. Now, if you've got a tail to the left, that's called a left skew. It's also called a negative skew because the long tail is towards the more negative values. So that is another type of distribution that you might get. And again, if you look at this chart, it shows you a sort of a general shape of a negative skewed distribution. And you can see that the mean, the median and the mode are now not the same value. In fact, the mean is less than the median and itself is less than the mode. So this is why we needed to make that decision about which value of average to make. And this is now starting to point to why understanding the distribution might very well impact upon this decision. Just to complete this thought, here's an example of a positive skew, also known as a right skew, because the long tail is to the right, the long tail is to the positive values. Example of this might be the spread of the distribution of income in a large factory. Most people are around this sort of central block. You might have a few part-timers or cleaners that are getting very low pay, and then you have a dwindling number of people, foremen, managers, right up to the owner, who are getting the much higher salaries, and that will be a typical of a positive skew. But again, unsurprisingly, the mean, median and mode are not the same value, but this is now switched. The mean is the greatest value, followed by the median, followed by the mode. So I hope you realize that this was an important consideration to understanding the nature of your variable in terms of what kind of distribution does it come from. A large percentage of the time it comes from a normal distribution, but not always. So in summary, the statistical convention as regards p-values is if your p is less than or equal to or less than 0.05, i.e. less than or equal to 5%, then it is considered good enough to assume the result was not a fluke. Now, this p-value has not been calculated by you. It's been calculated by whichever test you did. The chi-squared, the t-test, the Mann-Whitney test, the Wilcoxon test, you name it. All of the tests spit out a p-value, and it allows you to at least make a statement, or a value judgment as to whether you can declare statistical significance. Now, I feel that this discussion is relatively straightforward because you have a nice number, this p-value, that you can just look at its value and say, okay, how big is it, how small is it, and then I can make some value adjustment, and then it allows me to compare with what they're saying in their conclusion, in their evaluation. Less obvious but becoming more common is the idea of the confidence intervals. Now, confidence intervals on a single measure are generally an expression of typically of precision, of repeatability, of reliability of a measure, but sometimes, and this is only when it's a confidence interval assigned to a difference, that's when it's related to something called statistical significance. So let's just unpack that a little bit. This part you will not find as easy. I've got a slightly longer portion of a video that I'll link to that discusses this in more detail. But like a lot of the topics we're looking at today, this is just a heads up on the concepts. Now, confidence intervals, let's see how they go. Confidence intervals are given alongside a measure of, say, an average. Now, an average, if you think about it, if I look at the average of my data set, at best, that is my estimation of the population value. We are pretty sure that it's unlikely to be the exact value of the population parameter. So I also want to give some sort of numerical indication of how good an estimation that average, that mean, say, is. And so I want a lower and upper value that sort of captures what the typical spread of could be of the true value of the population value. So we calculate the confidence intervals using the sample mean, the sample spread, and the sample size. Okay. In many research papers, you'll see confidence intervals written like this. They'll say the mean equals 23. Now that number on the outside, 23, came from the data. So that was measured. But the value in the brackets, this 95% confidence interval, and do not be seduced by this 95%. It's always 95% because it relates back to that normal distribution. They've given you a 21 and a 25, the lower and upper values, but they've been calculated their theoretical values. And they're saying, look, it is the range of scores that are likely to contain the population mean, the true value. Now, again, that's not strictly 100% accurate, but it's good enough for our discussion so far. There are other levels of subtlety, but it gives us, if you wish, a plausibility interval, a range of plausibility with which we're saying how where our population value can be. Certainly, the closer those two values are together, the more confidence we're going to have in that measured value, say, of 23, or you could say it got a higher level of precision. Now, those of you who did science back in the day, you might have done experiments where you plotted error bars, in your graph book. Now, that is the same sort of thing as going on here, where the middle dot is what you measured, and the upper and lower values are an indication of the uncertainty, the fuzziness of your measurement. Now, if I just put that particular diagram horizontally, it'll allow us to do something quite useful, and that is to visualize a little bit more about what's going on. So for a single value, the confidence interval can be thought of as a measure of precision. The wider those bars are apart, the less precise; the narrower they are, the more precise. So where is it going to help us for statistical significance? Well, you just see, here's the same diagram, but now I put a number line underneath so you can see how this works. But let's introduce a second measure. Okay, so let's have two values, say a before or an after, or group A and a group B, and then see if we can develop or extract a single confidence interval that somehow summarizes that difference. So here's one experiment. Now I've had to put one above the other so they didn't sort of collide. Group A had a mean of 23 and group B had a mean of 26. Well, they're clearly different, and I want to know if that difference was due to fluke or not. But with their confidence intervals in place, you can see visually there's an overlap between the two groups in terms of their confidence intervals, I can tell straight away that that experiment is not statistically significant. If I compare it and contrast it with a different experiment with the same average values of 23 and 26, but now with a much more precise, much tighter set of confidence intervals, you can see how there is clear blue water, there's space between the two. They don't overlap. So I can see visually that the experiment on the left was statistically significant. Now, unfortunately, in the research papers, they do not give it like this. They do not give it diagrammatically, which is a real shame. So we need to sort of do a little bit more work here. So just hang on there and let's see what we can do. But if I've compared that more, that higher precision level, the one I'm claiming was statistically significant, I can say, right, I can see that my difference is 3, 26 minus 23, fine. And to get my confidence interval, I'm thinking, okay, I'm looking at differences. Well, I look at my upper confidence interval for the 26, which is 27, and I take away from that the smallest number out there, which is the 22. So the largest value of difference, 27 take 22 is 5. The smallest value of difference would be 25 take 24, and that explains, hand-wavingly, why my confidence interval for my difference in that case is 3. The reason I can look at that confidence interval of difference and still say instantly that is statistically significant is because that plausible range between 1 and 5 does not include the value 0, because in research, quantitative research, we very often have this idea of the null hypothesis, which is where we'll say a difference of 0 is, what we're trying to test against. If I look at that confidence interval of the differences, you can see on the number line below, 0 lies outside my 95% confidence interval. So I can say my results are statistically significant. If we compare and contrast that with that less precise measure, again with 23 and 26, and I do the differences again, I can see, okay, difference is 3, but now the greatest level of spread is 28, take away 21, that gives 7, but the smallest would be 24, would be 24 take away 25, which would be -1. So that is, I wonder if I've got this correct. 25 take 25. Yes, it is, because I'm doing the upper minus the lower. Anyway, I'm not going to worry too much about that, only that my difference, you can now see, is 3, but with my confidence interval has a lower value of -1 and an upper value of 7. The point is valid whether my maths was good or not, and that is 0 is within the 95% plausibility range. So the null hypothesis cannot be rejected because 0 is a plausible value of the population parameter, even though with our sample we measured the difference of being 3. So if you see a sign change, a confidence interval going from negative to positive, it tells you that there must be a 0 in there, in that inert number line, and therefore we cannot reject the null hypothesis. We cannot declare our results to be statistically significant. Like I say, this is one that might take a couple of reads. This is one where you might think, okay, I'll come back to this another time, or what worry about it now. I personally prefer p-values because they're just so much easier to spot. There was a real shift in fashion about 10 years or so ago, where they felt that there was more information carried in confidence intervals. Clearly there is, because there's more numbers, but I feel that you have to do a bit more work and it can more easily feel ambiguous. But at least we've started to acknowledge that inferential statistics is built upon the idea of statistical significance, either as a p-value or as a confidence interval of difference. Now, I've mentioned in passing that there are many tests, so let's just have a little look at the tests. The researchers need to wisely choose the correct test. Just as in descriptive statistics, you had to decide, well, what is the correct measure of average that I should be using, or the correct measure of spread should I be using. The same here. So it comes down to a series of decisions that I have to sort of make. So this is a paper I found from Green and Olivier, which I believe I put as a reference at the very back. And it is an example of one flowchart, a decision tree, if you will, that helps researchers select the most appropriate tests for their purposes, for their research. And now this was back in 82 when there wasn't much in the way of computing power. So believe it or not, even though this looks complicated, believe you me, this is way simpler than some of those you might see in the textbooks. You have these tests occurring at the end of these decisions. So most of this is occurring if you have a series of differences. If your data is only nominal, remember it's called categorical, there's only one test available, the chi-squared. If you're, say, looking at, say, two measures that you've tested, say, like, for a class you've done an English test and a maths test, then you're looking for correlations. You've only got a choice of two, Pearson test or Spearman test. But most of the interesting stuff is where you're looking at differences, either before and after, or group A against group B. And you ask yourself a series of questions. Once you've said, okay, I'm looking at differences across groups, the first question you ask is, well, how many variables are you measuring? How many outcome variables? So if it's one, I go down this line. If it's two, I go down this line. Well, if it's just one variable, the more simpler measure, the next question is, well, how many experimental conditions have you got? Well, that's another way of saying, how many groups have you got? If I've only got two groups, I'll go down this line and then it'll say, okay, is it a within or a between group measure? Well, within is a classic before and after, and between is that classic group A versus group B. Now, before it gives me the test, the t-test related, Wilcoxon, etc., there's one further question, and that is your data parametric or non-parametric? And this occurs for loads of these, not all, but loads of them. So we do have to think about that. You'll see decision charts like this, and if you yourself are doing research, you would almost certainly seek statistical advice as to what's the most appropriate test. But it is quite a good idea to at least have a sense of the fact that these tests aren't plucked out of the air. They're not chosen because I fancy doing this. You've got to choose the right tool for the right job, the right test for the right research design. You'll often see the research papers ANOVAs, and ANOVAs occur when there's either more than two groups or more than one variable being measured. And ANOVA just stands for analysis of variance. I do not want to do a deep dive on this, merely to, again, describe some key jargon like variables, jargon like within and between, jargon like parametric and non-parametric. All important stuff for us to stand a chance of being able to make sense of what's going on in a particular paper, or indeed how we're going to position ourselves with our own research once it unfolds. So the final sort of concept I want to discuss with you is this idea of, well, what do we mean by parametric or non-parametric data? It has to officially satisfy four conditions. The data, or the variable, has to come from a population that is normally distributed. Now, there are tests for this, so we don't just have to sort of intuitively know it, but sometimes you can either know this from the literature or you can run a statistical test yourself. Second condition must be that the data must be at that higher end of the hierarchy of data types. It must be either interval or ratio level data. If your data is ordinal, it instantly fails the parametric test, and therefore you can only use non-parametric tests. But as we saw in that flowchart previously, there's plenty of non-parametric tests out there, so not a problem. It's just that we all want to use the parametric tests because they are more sensitive, they are more likely to give us a low p-value. But it would be dishonest just to use them because of that, because if our data isn't strong enough to warrant using them, then we might end up with a conclusion in error. It becomes possibly a little bit dishonest. Okay, the third and fourth conditions are the variance, which is just the square of the spread, the square of the standard deviation, must be similar across the two groups. Now, this is quite a flexible one. Most textbooks say, so long as they're not 3 times bigger or smaller, then they can be considered similar. So that's a very generous one. And the final one is the data must be continuous. I made a mistake here. I said put rather than continuous, rather than discrete. Let me just correct them on the fly. So the data must be continuous rather than discrete. Okay, we've got our 4 conditions. Now, I used to think, right, these are rules set in stone, and paper after paper I'd come across where I think, well, I disagree with it. Their data hasn't been demonstrated to be normally distributed, or their data I feel is discrete, so they they've made a mistake. But I then started to get a feel as I read more and more research that these rules are relatively flexible. So for example, to take one example, that last point, your data must be continuous. If I'm marking students' assignment, so on a scale of 0 to 100, that's not quite true. Typically, you don't go below 20 as a mark, and you rarely go above 80. So it's on between 20 and 60, 20 and 80, sorry. But that's a range of about 60 values. But there are 60 values of which I only ever give whole numbers. I do not give fractional. No one I've ever come across does so. So it feels like discrete. It also feels like ordinal level data. However, because there's such a wide variety of numbers, say from 20 to 80, you can say, look, if you look at it a bit skew if, it behaves pretty much continuously. It behaves pretty much, if you can demonstrate this with a distribution that's normal, possibly. But, you know, the parametric tests, typically the t-test and the ANOVA test, are what's known as robust, in that they are quite forgiving for reasonable, modest levels of discrepancies between these 4 rules, and, you know, whether it's not quite the same. So if your data is nearly normally distributed, that's fine. If your data is interval or ratio, but it was discrete, but there was plenty of scope, plenty of range of values, then that's kind of okay. That third one, or the third one down, already has that built-in generosity anyway. So that's my discussion over. Obviously, I could have gone far deeper in many areas, but I think that was good enough for a starting point of the concepts of statistics within quantitative research. As I say, I'm going to point to some further videos to allow you to go to the next step. But it's only a little bit, pushing a little bit further, but hopefully it'll get to a point where you think, right, I can now dare to start to look at some of those entry-level research and stats books to sort of help further my understanding. But I did want to mention software. Now, because I work in what was the Faculty of Health and now is the Health Education and Life Sciences, I'm used to using a piece of software now owned by IBM called SPSS, which stands for Social Statistical, what was it stand for? Is it statistical processes in the social sciences? Doesn't sound right now. I'll worry about that later, and we can always look that up. But SPSS is very common. Here at BCU, we have a site-wide license for this. It's fine. Students and staff can go to ICT, look it up, find it, download it. We have a 1-year rolling license for it, so you'll be given a password which then runs out a year later. Fine. The downside is if you don't have access to this in your institution, then you're going to have to pay for it. It's not cheap. And as I say, it typically it's not cheap. And it has this idea of, you know, a time limit on it. So there's a downside there. Another downside is it can feel very complicated, certainly on a first look. Plenty of YouTube videos out there on it, some very good books on there as well. Regarding that, I'll mention at least a couple of books in my description, so that if you want to get into using SPSS, you can do so. The second one is one that I think a lot of us would like to migrate towards if we can, using Excel. Now, Excel is spreadsheet software. It was never designed as software for data analysis. But in recent years, the producers of Excel, Microsoft, have started to input something called a data analysis pack, and that is slowly but surely growing in scope. So now you can quite easily perform things like correlation tests, you can perform t-tests, you can perform ANOVA tests. It is not good yet for non-parametric tests. You can do it, but it's very faffy. There are others out there, Minitab, GenStat, you name it, lots of different pieces of software, commercial software that you can buy. I've started in my late years to think more about doing it yourself, either using Python or R. Now, for most people, this is not an option you want to even consider. However, they're both free. They're publicly available open source pieces of software that you can then and there's been lots of collaboration out there in the communities of both Python and R, where they have created subroutines libraries for statistics. So in Python, for example, the one I'm learning at the moment, it's quite straightforward. Once you've seen some examples of how to input data, how to output data, there's built-in functions for graphing your answers. There's built-in functions for working out certain simpler statistical tests. But the beauty of it is that you can build up your needs specifically for your own piece of research, rather than to learn something humongous like the SPSS or fight with the limitations of Excel, you can demonstrate your own understanding and reflect and learn, as it were, the underlying statistics. It may not be for everyone, but as I say, I've got one colleague who did his entire PhD and he just learned R and then went with it, and I'm seeing more and more in the scientific community people are using Python. So it's just something to think about, but certainly you've got to find a piece of software that does what you want, get the support, get the training up and running, and there's YouTube videos on all of these plentifully out there. So obviously you would avail yourself of that. So hopefully at least you think, okay, that's a step that I will have to take, but there is support out there for it. Finally, and some of these I will put as actual direct links. I've got a 5-video playlist which goes into a deeper dive on reading a research paper. So it goes into pretty much everything I've said today, but in a slightly deeper way. I've given you the link there to the SPSS download. That's obviously if you're a BCU student. Also, if you're a BCU student, there's a link to our Moodle page. And within our Moodle page in the ADD, I've got a whole section on resources, which is a direct link for yourselves. And then the Python software and the R software, the download ones, as I say, I'll put those on there as well. I'm hoping you found this of some use, and certainly for those of us where we had a sit down together, and those of you from BCU who are watching this, I did ask the question, what should we do now? Now, I gave my email at the very, very beginning of this presentation, so it's something which I very much would welcome your thoughts on this. Should we sort of develop some sort of community of practice or self-support group moving forward? I'm in conversation with the library about whether we might do a wider range of sessions. I have in the past done workshops on SPSS, etc. These are things that we can explore later. But I will leave you with the official references that go with the talk. I think actually some of these didn't appear in it, but they're references and further reading. Some of these are very, very useful. The book by Tricia Green, How to Read a Paper, The Basics of Evidence-Based Medicine and Healthcare, now in the 6th edition. That's a very student-friendly book. The book by Peacock, a bit more involved, but again, it's very, very useful and I feel very clear for those of us trying to make sense of medical statistics. The one book that's quite old now, Read and Bore, I just cannot praise it high enough. It's a very slim volume, very readable, but it talks you through, this is the days pretty much before computing, but it explains in great detail, or rather in sufficient detail, what's going on with the more basic tests. So, something to maybe think about. Anyway, I'm going to sign off there. I hope you found that of some use and that didn't go to sleep too much. And I'm going to stop the recording and hopefully catch up with some of you at another time. All right, thanks a lot and take care.